Hi everyone, I am Kaninika. I am an intern at MathWorks. In this video, I will be talking about Simulink IO on Arduino. I will also be showing demos for all peripherals on Arduino Mega 2560. So what is Simulink IO? Simulink IO basically provides a quick way to connect to and control Arduino inputs and outputs from Simulink. You can read values from peripheral sources such as ADC and write to peripheral actuators such as PWM. It is similar to the MATLAB solution that we ship with Arduino. In Simulink IO, whenever the user clicks play, we build a server that is flashed on the hardware board, in this case, Arduino. Once flashed, you can start reading or writing right away from Arduino. You can stop the simulation, change your model, and rerun it without any waiting time. The biggest advantage of Simulink IO is that it provides instant gratification to the user. With Simulink IO once set up, you can read, write to Arduino immediately without waiting for a build or download. If you wish to change your model, hit stop, change your model, and click run. You should get started right away. This is useful during early stage of your design in which you might want to update your model regularly. To work with Simulink IO on Arduino, you need to first install the corresponding support package. For that, go to Add-ons, Get Add-ons, search for Simulink support package for Arduino, and install it. I have already installed it. On installation, you will now have a toolbox called Simulink Support Package for Arduino hardware, in which you can find all your hardware peripherals. You can simply drag and drop them. You could also type on the Simulink window to get a block. The first demo that I will be showing you is for digital input output. The first thing you need to do is configure your model. For that, go to Model Configuration Parameters, search for the Hardware Implementation option, choose the hardware board. In my case, I'm using an Arduino Mega 2560. Go to Target Hardware Resources, go to Simulink IO, and check the Simulink IO option. Right now, it's already checked. So I will be demonstrating the blinking of an LED using the digital output block. I'll do it in two ways. One is automatically using the pulse generator block, and the other is manually using the manual switch block. So let's do the first thing. Take a pulse generator block and a digital output block. Connect these two. Set the pin number in the digital output block to 13, since that is the LED on this board. You can also go to the pulse generator block and set the various parameters. Next, we need to go to the pacing options. So Simulink Pacer basically tells your Simulink model how fast it is supposed to run as compared to real time. Right now I have set it to 1. Let's try running the model. You can see the blinking of the LED. It is on for 50% of the period and off for the other 50%. The period is set to 6. Next, let us modify this model. Click Stop. Comment the initial model out. Let us now manually try to blink the LED. For that, we first need a manual switch block. The two inputs to this should be 0 and 1. Connect two constant blocks to this switch. Set one value to 0 and the other to 1. The output from this manual switch block should go to a digital output block. Again, you need to set the pin number of this block to 13. Now let's run this model. You can see that it did not take time to change the model and rerun it. This is the biggest advantage of Simulink IO. You can see that the LED is glowing and now it is off. It's glowing and again it's off. My next demo is for the ADC and PWM peripherals. I would first be generating PWM on my board. The output from the board has been connected to an RC circuit. The frequency of the PWM is set high so that the voltage across the capacitor would be the average voltage of the PWM wave. This voltage can be read using an analog input block. Pin A0 has been connected to the capacitor for this purpose. Now let us make the model. We first need a PWM block. The input to this is the duty cycle. The pin number is 2. Since this is the pin which I have connected to my RC circuit, you can see that the block accepts values between 0 to 255. So 0 would mean 0% duty cycle and 255 would mean 100% duty cycle. The reference voltage for this board is 3.6 volts. Let us set the input as 255. Next, we need an analog input block to measure the voltage across the capacitor. Let us connect this to a scope block to observe our voltage. Let's change the pin number to pin 0. Let us try to log this signal and then we could observe it using SDI, that is Simulink Data Inspector. Let us now run this model. We can view the voltage on the Simulink Data Inspector. Since the input is 255, that would mean the maximum duty cycle. To make more sense of this, let us go to limits. Set the normalized y-axis limits. We can see that the output voltage is near 1. That is the maximum possible voltage that can be generated by our board. While the model is running, we can also change the input. Let us make it 128, which is roughly half. We can see that the average voltage has dropped to 0.5 as expected. Hence, such values can be changed during runtime and the results can be visualized immediately. My next demo is writing to and reading from an SPI EEPROM. I'm using the IC 25AA080C. The page size of this EEPROM is 16 bytes and the address size is 2 bytes. First, let us go to the library and get a SPI write-read block. It is found in the Simulink support package for Arduino. You can drag and drop the SPI write-read block. To write to this particular EEPROM, the first thing you need to do is give the write enable command. That command is 6. The way an SPI EEPROM works is that whenever you write some data to the EEPROM, some data is also returned by the EEPROM. Hence, the output will be the same number of bytes as the input. Let us connect a display block to the output of the SPI write-read block. Next, let us write to this EEPROM. For that, you first need to give a write command, followed by the address and the data bytes which you wish to write. The command for writing is to. The address I'll be writing to is 00. The data could be anything. Let's say I give a 1, 2, 3 here. Again, we need to connect a display which will read as many number of bytes that I have written. After writing to this EEPROM, let us try to read from the same location. For that, we first need to give the read command followed by the address and then as many number of zeros as the number of bytes that you wish to read. So let us change the command value to 3 and let us change the last values to 000. Again, we need to connect a display block to the output of our SPI write-read block. Our model is now ready. I will just expand these display blocks so that you can clearly see the values returned. Before we run the model, make sure that the data type that you are entering is a uint8. All your inputs must be of the uint8 type, since this is the data type that is written internally. Next, choose the slave select pins in the block. In my case, the slave select pin that I have connected to my EEPROM is digital pin 8. Now we can run our model and observe the output. So, the values returned on writing are junk values. You can see that the output has become 1, 2, 3 as was written in the SPI EEPROM. The initial values are again returned by the EEPROM since it has to return the exact number of bytes that have been written to it, although the first 3 values are junk. My next demo is I2C interface to MPU 6050 triple axis accelerometer and gyroscope. The MPU 6050 is a 6-axis motion tracking device that combines a 3-axis gyroscope, 3-axis accelerometer, and a digital motion processor. It contains 3 16-bit ADCs for digitizing the gyroscope outputs as well as for digitizing the accelerometer outputs. I will be communicating to the sensor through I2C. I will show you how to work with the accelerometer unit. The first thing we need to do is sensor configuration. This is something which only needs to run once. Hence, I have made the following arrangement. This is a delay block. The initial condition is set to 1. The input to this block is 0. and the output from this block goes to an enabled subsystem block. Hence, after the first sample time, the input to the enabled subsystem block would become 0 and this will no longer be enabled. Inside the enabled subsystem block, I have configured two of my registers. The first is a power management register. The address of this is as follows. The first is the address of the sensor. The power register allows the user to configure the power mode and the clock source. I have set the input to this register as 0. 0 means that I am using the internal 8 MHz clock on the sensor. The next register that I have configured is the accel config register. This is the register address. I have set the range of my accelerometer through this to -2G to +2G. The command for this is 0. Now coming back to the main model, I will be reading data from the accelerometer data register. This is the address of the register. The following is the format of the data that I will be reading. Internally, the sensor has 16-bit ADCs for the accelerometer unit. This means that the output will be in the range -32768 to 32768. That is an int 16 number. Internally, there are three 16-bit ADCs for the three axes. Hence, I am expecting 3 int 16 outputs. Hence, I have used a demux. The three outputs from this demux are the data of the x-axis, the y-axis, and the z-axis. You can also connect outputs to log your signal. Now, we expect an int16 output data type, since the I2C read block only has uint8 and uint16 as the data type options. We can connect a data type conversion block and set the data type as int16. So let us do that. Let us add a data type conversion block. Set the value of the data type in it as int16. Let us add it here. We can now run our model. Since the maximum acceleration value is set to 2g and int16 has a limit of around 30,000, the value of 1g will correspond to half of this, that is around 16,000. We can observe this by simply moving our sensor. We will keep our sensor still and point the axis in the up and the down direction. Then the only acceleration that the sensor would sense would be due to gravity pulling it down. Let us try moving the x-axis. Right now, it is parallel to the ground. Hence, it reads a value of 0. Let us now point it in the upward direction. We can see that the value is close to 16,000. Let us now point it in the downward direction. You can see that the value is close to -16,000. In the same way, we can also experiment with the y and the z axis. Again, you can see that the y-axis is parallel to the ground. Let us point it in the upwards direction. You can see that the value is close to 16,000. Now, let us put it in the downward direction. The value is now close to -16,000. Similarly, we can also experiment with the z-axis. It is now parallel to the ground, now in the upward direction, and now in the downward direction. The following are the use cases of Simulink IO. The first is sensor characterization. An excellent example for this could be the line follower. Let's say you're designing a line follower robo. Before you actually run your model on Arduino, you might want to check your sensor data. To do this, you can first build another model just to observe the kind of sensor data you're getting by keeping your bot on the black as well as the white lines. Later, you can put your original model on the bot and make it run. The best way to go about this would be to use Simulink IO. With Simulink IO, the user can model solutions that don't have a tight control loop or models that don't have a high sample rate. For models with high sample rates, building and deploying the model is the best way to proceed. So, what is the difference between external mode and Simulink IO? External mode is used to tune parameters and log signals of a deployed Simulink model. After your Simulink model design and deployment to the hardware, if you would like to tune and modify your algorithm, use external mode. In external mode, the Simulink model will run in real time on the hardware and provides a way to log and tune the Simulink algorithm data in real time. Simulink IO, on the other hand, is non real time. Data is acquired using the device driver blocks, and all other Simulink blocks execute on the PC. That is all for this video. Thank you for watching.